Welcome to grade 12 physics. We're going to do work, energy and power. This is lecture number 2. In this one we're going to discuss a few standard cases. I want to start with a simple one. We've looked at a block on a slope and forces. Let's just look at lifting a mass, shall we? Here it is. Here's our block. We're going to be lifting a mass. Okay. Lifting a mass. All right. Now, in the problems we're going to do much later on, we're going to put some time and some curves. They could even use a whatchamacallit curve, a VT graph or whatever for this. But don't worry about it. The process stays the same. The first thing we do is we say, right, here is my mass. What's the first thing we do in physics and mechanics? Is we put in Fw is equal to mg. Okay? Now, if I am lifting it, right, there it is. Let's just get there we go. I'm lifting it, okay? And therefore, I'm going to have a tension in the rope going up, am I not? My next thing is to say, okie dokie then. I've got a tension going up, just checking. Well, let us look at case 1. Case 1 is when T is equal to mg. Now, essentially, we are recapping previous grades, previous levels work. If the pull up is equal to the pull down, it means I'm in equilibrium, doesn't it? It means that as it moves up, V up there and V over here, it means that V final is equal to V initial. Okay? It's moving with constant velocity, correct? It's going at a constant velocity because I'm pulling up with the same amount as coming down. It is in equilibrium. Recapping some of the previous work that we did. Now, if it's in equilibrium, it means that the velocity is not increasing. Well, therefore, there is no acceleration. Correct? If something's velocity stays at 60 kilometers an hour there and here, it hasn't accelerated because acceleration is change in velocity over change in time. Well, we can also look at it. Now let's have a look at, before I say that, let's have a look and ask the question. Is there an F net? No, because T minus mg equals 0. Therefore, no F net. Therefore, it equals 0. ma, therefore, acceleration equals 0 as well. It means that in this case, it's going to be only an increase in potential energy. Let's just for the heck of it, let's continue our foray into this one. Just for completeness, just so that we understand what we're saying. Because our problems, this is all the problems we're going to get, are all like this. Okay? They're exactly identical to these. Let's look at this problem for, let's take it and we say, all right, let's say the tension up, let me just scroll it down slightly. Tension up was equal to 60 newtons and the weight down is equal to 60 newtons, right? But it is going up, right? It is physically here. It is going up at a constant speed. So my block is moving up. What is it gaining? It's gaining potential energy, isn't it? So therefore, what can I say? I can say that we are gaining EP, right? EP is therefore going to be a positive number, right? Because you're going to have mg times h final minus h initial, and h final and h initial, basically hf is bigger than h initial, isn't it? Why? I was here, let's say I was at 0, and now I'm at plus 10. This is h final, this is h initial. So if I take that, I'm going to get a positive answer. I am gaining potential energy as I move up, all right? We know this from previous, right? Because the total mechanical energy while I'm doing it, let's just recap that as well. All right? Let us say total mechanical energy, total mechanical energy is going to be EP plus EK. Right? That is the total mechanical energy. Remember we discussed you get electrical, chemical, all kinds, nuclear, all kinds of energies are going to come into this. But we're only talking about mechanical at this stage. So it's potential plus kinetic. Okay. Now, if I'm thus moving up, can you see that the work done is the change in potential energy, isn't it? So let's look. Work done is equal to change in EP, which is going to be mg times H final minus H initial. That is all the work, and in this case the work done is the force times the delta x up, and the force is going to be equal to, in this case, my tension in the rope times delta x, which is going to be, if I just use the numbers that we've got there, I think I used, yes I did, I used a 60, come on, 60 times delta x. Please, I am using, just as I said up here, all right, I am using this here, H final, H initial. This is also delta x, isn't it? The displacement is just in the upwards direction. So, I now say to you, okay, therefore, let us look at another case now. Let us take case 2. Okay? This is all you need to know. Just logic it out. Please, with these, you can't just bang in numbers and get an answer. It's not going to work. Case 2. I'm doing the same job. All right? There's my F. I do wish it would not do that on me. FW is equal to 9.8 times mass, or let's just call it mg, shall we? So we've got mg like that. My next task is to say, okay, I have got T going up, and in this case, T is greater than mg. What does that mean? That means that we are accelerating because my up pull is greater than my down pull, which means, is there an F net? We always ask the question, is there an F net anywhere? If it's accelerating up, there must be a net force up. We say, therefore, F net is going to be equal to T minus mg, which is actually equal to ma. All right? Therefore, we have an acceleration upwards because I'm pulling up with more than I'm pulling down, right? So we said this was 60 newtons down. Now let's take this as 100 up there like that, okay? So if there's an F net, my body is accelerating upwards, right? It's accelerating upwards. Now, if it's accelerating upwards, it means that V final is greater than V initial. The velocity here is greater than the velocity there because it's accelerating in an upwards direction. Okay, well, that's cool. So what does that mean? It means, have another page. Now, if this is the case, it means that let's have a look at my EK, shall we? EK. Change in EK is going to be equal to a half mv final squared minus a half mv initial squared, correct? What does that mean? It means that I can factorize a half m. It's going to be v final squared minus v initial squared. Can you see that? Therefore, my change in kinetic energy is positive upwards. It must be because my velocity final has increased. Therefore, I have had an acceleration upwards. Right? A is positive up. So I have accelerated up. My kinetic energy has increased. And the work done is going to be equal to F net times delta x is equal to the change in EK. Right? We know that. Which means in this case, it's going to be equal to, remember I had 160 down. It means that my work done is going to be 40 times delta x, which must be equal to delta EK. What about the MGH? Has that changed? Yes, the MGH has changed because the block has moved upwards. Therefore, I can also say that my delta EP is going to be mg times delta x as well, isn't it? Right? And in this case, you can tell that that is going to be the balance of the force, which was the 60 delta x. Okay? The total mechanical energy is we'd add the two together. Right? All we've done is we've just split them apart into two logical sections. The one force, the F net, has increased my kinetic energy because it's done an acceleration. Why? Because F net equals ma. That's the force that's accelerated me. What is my next thing is, there's my EP and there's my EK. Okay? Now, what happens if we take the next logical step and let us say case 3. Case 3, I've been using, I think, Roman numerals, but it doesn't really matter. Case 3, what if T and mg, what if T is less than mg? If T is less than mg, what does it mean? Well, it's quite simple. It means that the object has my velocity initial and my velocity final. There's an F net here of mg minus T, isn't there? In other words, my tension isn't enough to hold it up. So it's going to start an acceleration, okay, is going to be that way, isn't it? I'm either going to slow down or I'm going to accelerate downwards. And what does it depend? It depends on where I started. If I'm at 0 velocity, I'm going to end up with a velocity, I'm going to be accelerating down. Correct? If I was moving up with 20, okay, and the force T slackened, it means that I'm going to slow down. I'm still going to move up. The lift is going to keep moving up, but then it's going to slow down to get to the next floor, right? We accelerate, constant velocity, decelerate to the between floors. Okay? And that is as simple as that. This is in fact how we do it. All we do is we say all these different cases over here, there they are. So let's just have a look. VI and VF. Remember, we are slowing down. Therefore, VF, okay, must be less than VI. All right? Because we've actually removed energy from the system. We have slowed it down. Let's take a quick example. Here we go. We've got a block. All right. It's sliding along over here, and here it hits a rough surface. This is an example that's very often used. It hits a rough surface. So if it's sliding along here at 10 meters per second, and it hits a rough surface, what happens? Over here, we have FF, which is the friction, correct? This is an externally applied force, which slows this down. So I've got EK here, okay, initial, and I've got EK final at the end. Let us say that the block stops. Therefore, it's 0. Therefore, it has lost, I'm putting it in inverted commas before everybody shouts at me, okay, it has lost energy. Well, energy from the law of conservation of energy cannot be lost. It is merely converted from one form to another. So what has happened in this situation? It has been altered. It's been changed into, we've lost it, the friction. So if friction multiplied by this delta x here. That is the external work that's been done, isn't it? That force over that distance has removed the energy, right? So, for example, if we measure that distance, we can work out the frictional forces. If you know what the frictional force is, you could work out the coefficient of kinetic friction mu k. Because, why? Ff is equal to mu k F normal. And F normal you know. Therefore, you could, and Ff, you could work out mu k. So, on all of these things here, the critical part is in effect to draw the diagram, label it with what we know, and then put in the forces that are acting. Because if there's a force that's adding to it, that force is going to give you an F net. F net means that we've got an acceleration in a direction, or we've got a deceleration or a negative acceleration. Let me put it that way. Okay. Now, I'm just going to leave this piece because there I've got another few cases that we can do. The other cases are going to be on slopes. All right. So, do you know what? We can do them into this video. I think because this is a general case solution type oriented video. So I want to have a look here now, and I say, all right, case one, let's have a look. This is applying to a slope now, okay? This is applying on a slope, and what did we say? We said we put in mg, which is the weight, and then we put in our components, whereas this one is going to be m, and that's theta, remember, theta there, mg sine theta, mg cos theta, F normal over there, and in this case the block is moving up, F applied that way, and F frictional force down, and we've got over here mg sine theta, right? We always put that in there. Now, what if, and here we go with our scenario planning, right? What if F applied, okay, is equal to, so I say, what if forces up slope equal forces down slope? Force up equals force down. It's in equilibrium. Remember this? Equilibrium, right, like that. Which means, once again, there is V initial equals V final. It's going at constant velocity. Okay? Up or down, doesn't matter. All right? All we know is that the forces pulling it up the slope are equal to the forces down, or the forces down equal to the forces up, whichever way you want to look at it. All right? Now, in this case, this must be moving up slope, right? Because friction I've got is that way. Right? So, in this thing, the work energy, it's going to be, let's have a look. I can say, let's have a look here. Okay, in here, there's no F net because I say F applied. Remember, we've got this formula from the previous, minus mg sine theta minus ff, okay? That there times delta x must equal to change in the EK. Remember that formula? Well, look, F applied is equal to those. It's balanced. Therefore, this is 0. No F net. So therefore, no change in EK. Yes, we're going to have an EP change, which is our mg sine theta delta x. Okay? So in that case, all I say is my delta EP is equal to mg sine theta delta x times delta x, like so. Right? That's quite straightforward. What if the force applied is greater than the force down? Okay? We said if F applied up is greater than down, there's an F net, therefore the kinetic energy will increase up the slope, and we will gain kinetic energy, and we'll gain potential energy as well. So what would we have? We would have F applied, this would be case 2. Okay, case 2 is going to be F applied greater than mg sine theta plus the force of friction, right? Because this is F up the slope, this is F down. So F app minus mg sine theta minus FF multiplied by delta x must be equal to delta EK. Okay? And I will have an acceleration up the slope because I'm pulling up the slope more than I'm pulling down. Simple as that. No worries. That's all we have to do with it. Right. Now what's the next one? The next one, obviously, in this situation, once again, I've got my EP, okay, which is going to be the same story as always. Okay. Up the slope, the energy, yep, we've got that. And we said it will increase. Let's have a look. Now let's have a look at case 3, okay? Case 3 on a slope. Always go back to your slope. And I've said here, what if F applied, if F applied is less than mg sine theta plus the force of friction, right? That means that the F up the slope is less than F down the slope, okay? It means that the block may be turning. It means that the block might be going down. You would have to check and see if FF, because remember, if the block is going to go down the slope, there's my F applied, right? Here's my mg sine theta, correct? Is there. What is this here? Now, if this is bigger than that and that, my FF might turn. If mg sine theta is still bigger, it then means that my F net is going to be mg sine theta minus F applied minus FF times delta x must be equal to delta EK. Right? This is my F net. My F net is now downslope. I'm accelerating. In other words, the force I'm applying, remember from the stuff we've done before, the force I'm applying isn't enough. It's pulling me down the slope. I can't hold it. It's pulling me away down the slope, right? So in all of these situations, okay, what would our recipe be for this lot? We'd say, first of all, let's just try and come up with one. Recipe, first one, would be draw it. All right? Draw it. Label what's given. Okay? Show what's given. 3, all right? Put in the forces. Put in the forces. Show forces. Remember, weight first. Okay? Put that in first. Okay? Then, look at friction. Is it acting up or down the slope? Depends on which way the body is moving. If our truck is going down slope, right? Can you ever imagine when a truck would have to actually put a foot on the accelerator to go down a slope? Of course, yes. It's not always the case that it will run away down the slope. Why? Because the friction acting against the truck could still be quite substantial. All right? So, yes, sometimes you still have to put your foot down to go down a slope. Because if you took your foot off, the friction will just slow you down until you come to a stop. Right? So, in all of these, just go back to what we did in the previous ones with things on slopes and look at it carefully. Because that's all you have to do. All right? Then we say, look at EK. Okay? Do EK calc. EK calc. All right? In other words, you find your F net delta x must be equal to delta EK. And depending upon what they've given you, they might have given us the delta EK. They might have told us a half mv final minus v initial. They might have told us those and asked us what's the distance. But if you've written it down and you've labeled your diagram, you'll see it. All right? The last one is then do your EP calc. 6. Look at EP. Okay, EP is going to be mg sine theta delta x. Mg sine theta delta x is equal to delta EP. Okay. They might have given us delta EP. They might have told us it goes up a distance of 10 meters. They've given you then that, haven't they? Right? And we can find out various other things from there. That, in essence, is how we're going to do them. I'm going to do a few calcs, okay? I'm going to do a thing on a level slope. I'm going to do something going uphill. I'm going to do a truck, I think, going downhill, accelerating downhill. There's a few that we're going to do here, all right, on this particular one. There's also a projectile motion that we're going to do as well. Okay, right. We'll be back and we'll do the next one. That's going to be some examples. And you'll see all I'm going to do is exactly what I just did here. I'm going to look for what case it is, and then I'm going to say, what have I been given and which way is this thing going? See you just now. Thanks for watching. Bye.